The explosively pumped flux compression generator, or EPFC, converts chemical energy directly into electromagnetic energy within microseconds. This process achieves instantaneous power levels exceeding those of conventional power plants by orders of magnitude. The fundamental principle relies on the conservation of magnetic flux, phi, defined as the product of magnetic field strength B and the area A enclosed by a conductor. An initial seed magnetic field is established inside a conductive coil, typically sourced by a capacitor bank. When a high explosive charge detonates, it rapidly deforms and collapses the coil structure. This mechanical compression drastically reduces the enclosed area A. Since the magnetic flux phi must remain constant in a perfect conductor, the magnetic field density B is forced to increase proportionally to the reduction in area. This rapid flux compression is the engine driving the immense current amplification necessary for generating a high-energy electromagnetic pulse. Establishing the initial magnetic flux requires a robust seed current, often supplied by a high-voltage capacitor bank discharging into the generator coil. This coil, known as the stator, is typically wound helically around a central conductive tube, the armature. The armature houses the explosive charge. For effective compression, the seed field must be maximized before detonation. A typical EPFC system uses a bank storing several megajoules, generating an initial current of tens of kiloamperes. The geometry of the helical winding is critical. It must maximize the initial inductance while ensuring the subsequent explosive expansion creates a clean sequential short circuit. Precise timing is essential. The explosive initiation must occur exactly when the seed current reaches its peak, maximizing the initial stored magnetic energy, which is proportional to inductance times current squared.
The detonation sequence begins at one end of the armature, propagating a high-velocity shock wave down the central axis. This shock wave causes the conductive armature tube to expand radially outward at speeds often exceeding 8 kilometers per second. As the expanding armature contacts the inner surface of the helical stator coil, it sequentially shorts out the turns. This action effectively reduces the length of the coil and the volume containing the magnetic flux. The rapid physical closure of the circuit turns transforms the generator from a high inductance system to a low inductance system almost instantaneously. This dynamic change in geometry is the physical mechanism responsible for the massive current gain, converting the kinetic energy of the expanding metal into electromagnetic energy. The current amplification factor in an EPFC generator is fundamentally determined by the ratio of the initial inductance to the final inductance. The governing equation for the current I is derived from the circuit equation voltage equals negative inductance times the change in current over time minus current times the change in inductance over time. Since the resistance is minimized and the change in inductance over time is a large negative value due to the rapid compression, the current I increases exponentially. A typical helical generator achieves current gains ranging from 10 to 50 times the initial seed current. If the initial current is 50 kiloamperes, the output current can peak at 2.5 megaamperes. This massive current surge is accompanied by a corresponding reduction in the generator's internal impedance, allowing the delivery of gigawatts of instantaneous power to an external load.
Extracting the amplified energy requires careful impedance matching between the generator and the load, which is typically a radiating antenna or a high-power switching element. The output pulse is inherently a single-shot event, lasting only tens to hundreds of microseconds. To maximize the radiated electromagnetic pulse, the generator output must be coupled to an antenna designed to efficiently radiate the specific frequency spectrum generated. For high-frequency EMP generation, a fast opening switch is often employed at the output. This switch rapidly interrupts the mega-ampere current flow, generating an extremely high voltage spike, often exceeding 1 megavolt, which is essential for creating the desired high-frequency, high-power transient pulse. While the helical generator is common, two other primary EPFC geometries exist, the coaxial and the plate generator. The coaxial generator uses a central explosive charge to drive an inner conductor radially outward against an outer conductor, compressing the flux in the annular gap. This design offers higher symmetry and is often used for driving plasma physics experiments. The plate generator, or strip generator, utilizes two parallel conductive plates separated by an explosive layer. Detonation drives the plates together, compressing the flux between them. Plate generators are highly efficient for generating extremely high magnetic fields, often exceeding 1000 Tesla, but typically deliver lower total energy compared to helical designs. Each geometry is optimized for specific load characteristics and pulse requirements. EPFC technology forms the basis for non-nuclear electromagnetic pulse weapons, or NNEMP. Unlike nuclear EMP, which generates a wide-area high-altitude effect, NNEMP devices are localized, tactical weapons designed for precision electronic warfare. The primary target is unprotected electronic infrastructure, including command and control systems, communication networks, and critical data links. The high-power microwave output generated by coupling the EPFC to a suitable antenna can induce destructive transient voltages in target circuitry. Since these devices rely solely on chemical explosives, they are highly portable and deployable, offering a significant advantage in tactical scenarios where collateral damage must be minimized compared to conventional explosive ordnance.
EPFC generators face significant operational constraints, primarily their single-shot nature. The device is entirely destroyed during operation, necessitating complete replacement after each use. Efficiency is also a challenge. While the energy gain is high, the conversion efficiency from chemical energy to electromagnetic energy typically ranges from 10 to 20%. Furthermore, achieving the necessary timing precision, measured in nanoseconds, between the seed current peak and the explosive initiation requires sophisticated firing circuits and diagnostics. Material science limits the maximum achievable current density, as the conductors are subjected to immense magnetic pressures and rapid heating, leading to plasma formation and eventual flux leakage, which limits the final energy output. The deployment of NNEMP weapons is governed by the laws of armed conflict, specifically the principles of distinction and proportionality outlined in the Hague Conventions. While EMP weapons do not cause direct physical harm to personnel, their use against civilian infrastructure is prohibited. Future development focuses on increasing the repetition rate, moving away from single-shot explosive devices toward reusable pulsed power systems, though these currently lack the energy density of EPFC. Research also targets optimizing the coupling efficiency to high-gain antennas and developing compact, high-energy density chemical explosives to further miniaturize the generator package for integration into smaller delivery platforms, such as cruise missiles or unmanned aerial vehicles.